More generally, we're going to say that an exponential function is a function q of t that's characterized by basically three things. We have an initial quantity, which we call q sub 0, q naught. We have a growth factor b raised to the t power. And just to generalize things a little more, and your text doesn't do this, a lot of authors don't do this, but consistent with the way we generalize other functions, I'm going to say also we can add a constant to this function. Now that could correspond, for example, if your initial quantity is a principal and this is a growth factor due to interest on an investment. Okay, you've got some money invested at some growth rate that gives you a growth factor, and this is what you get from that. This constant here is some treasure, some money, some dollar bills or some coins preferably that you have buried out in your backyard. Okay? Or alternatively, if this was a radiation situation, this could be background radiation. Okay? If this is initial radiation and you have a decay rate and so forth, you could have a certain background radiation that isn't affected by this decay. So there are all kinds of things that we can have here where we might add a constant. A temperature function. Temperature of a cooling object or a warming object, if it's approaching room temperature, C is going to be a room temperature. So there are a lot of situations in which we want to add this constant C. And if that happens, your graph is going to have an asymptote at y equals c, or at q equals c. Now, if c equals 0, of course, the graph has the t-axis as an asymptote. And let's look at that situation. Okay? We have some quantity, q equals q naught at time t equals 0. That's going to be the y-intercept of a graph of q versus t. And then, at some time, which we'll call t sub 0, we're going to have a quantity. Now I labeled this quantity carelessly. I labeled it q sub 0, and it's clearly not q sub 0. So I'm going to make that a q sub 1, and I'm going to make this a 2q sub 1. And we'll see what I mean by this in a minute. Okay, so that shouldn't be q0 and 2q0, because q0 is the y-intercept of this graph. Now, what we're really interested in is doubling time. So at time t0 we have some quantity q1, and then after some time, which we call t dub for the doubling time, we have double that quantity, 2q sub 1. And we can see that the quantity represented by the height of the graph here is doubled, or thereabouts, as we move over here. And of course, the clock time here is t naught plus t dub, the doubling time. The quantity that we have here we're going to call q of t naught plus t dub, because of course this is a function q of t, and t equals t naught plus t dub. So when t equals t naught plus t dub, we have q of t naught plus t dub. The quantity here is going to be q of t naught, because we have clock time t naught, and we're going to have the fact that this one is twice as great as this one is going to be represented by the equation q of t naught plus t dub equals 2q of t naught. So that this equation, q of t naught plus t dub equals 2q of t naught, represents the fact that the quantity doubles between clock time t naught and t naught plus t dub. Now, if q of t equals q naught b to the t, then simply substituting t naught plus t dub in for t, we get q naught b to the t naught plus t dub, because we replace the t here when we replace it here. And then replacing this t by t naught over here, we obtain q of t naught equals q naught b to the 2t. B to the t naught, sorry. I'm listening to some bad noises that you might hear in your tape that are being made by my recorder here. I'm going to have to attend to that in a second. In any case, we obtain this equation, and this equation is going to tell us what t dub is, because we're going to be able to solve it for t dub